The Weibull distribution is an extremely flexible, bounded, and continuous PDF, used widely in engineering and scientific evaluations, for example, product reliability, namely modeling failure times. Excel's built-in dist function has two shape parameters, alpha and beta, where alpha is a shape parameter, where less than or equal to 1 makes an exponential curve, between 1 and 2.6 is a right skewed distribution, and 3 is normal, and greater than 3.7 is left skewed. Beta is the scale parameter. It stretches out the PDF. Cumulative, when true, produces a cumulative probability, and when false, produces a mass density plot. Because there's no built-in Weibull.im function, X values are cumbersome to calculate in Excel. The parameter alpha and beta can be fitted using a scatter plot of the natural log of X, where X values are sorted, versus the natural log of minus the natural log of 1 minus the probability. The slope of the trend line in alpha and the intercept is used to calculate the beta parameter, namely the exponential of minus the intercept divided by the slope. In the example that we're looking at, the top 100 fields, Weibull's mode is offset from beta and log normal PDF modes. As we can see in the upper left figure, the Weibull distribution does a good job of matching the observed frequency data, the blue dots, and it extends to and no further than the maximum value that was put into the data. The log normal distribution in green perhaps does a better job of fitting to the observed data, but its right tail extends beyond the 100,000 limit of the input data. And the beta also does a good job, but it underpredicts the extent of the data. So let's move on to the Excel demonstration. Here's our worksheet for calculating the Weibull distribution. As I mentioned earlier, it's a bit cumbersome to make this calculation since there's no Weibull.im function. So we're going to have to calculate all the parameters out and then do a cross plot and determine the shape factors. So let's start by taking a look at our data. So here's our data here. Again, it's the same 100 top oil US oil fields. And I just sort them in this column. And then we just do a sequential set of numbers, I, and then we take the probability of I. So if I click on that, we see it's just the sequential number minus 0.05 divided by the count, which is 94. Then we take the natural log of the sorted value, and then we take the log times the minus log of 1 minus the probability of I, this value right here. And we do a cross plot. So if we take a look at the values, we can see we're just plotting up these two columns. At this point, we can calculate the shape factors. So we just take the slope of the log of the sorted times the log times the minus log of 1 minus the probability. That'll give us the slope. Then we can calculate the intercept. And again, it's the same two columns. And we calculate that out. And from there, we can calculate the beta shape factor, which is just the exponent of minus the intercept divided by the slope. With the shape factors in hand, now we can calculate the Weibull distribution. So it's basically the X value, alpha and beta, and then we say false because we want the mass density parameter. And that now gives us the opportunity to calculate the Weibull distribution, the orange line. And for comparison, I've put the beta in black and a log normal in green. Over here to the right is where I calculate out the shape factors for a lambda of 12 for the beta distribution. Basically, I find the most likely value by looking at the max of the Weibull.dist and do a X lookup to find what the X value is that corresponds to that. So now with the min, most likely, and max, I can do the beta. And to do the log normal, I've just taken the mu and sigma from our fitted log normal that we did in exercise 8. Down below, I've put a table of the descriptive statistics and some good references to look at for how to construct these tables. Also, on the very far right, I've added a little game you can play with where you can just change alpha and beta and see how the curves change. I hope you found this video useful. I'll leave a link in the video description. Thanks for listening, like and subscribe.